Hello and welcome! My name is Vedran, I'm a Microsoft Certified Master for SQL Server, and today we will optimize Delete Cascade. Delete Cascade is similar to optimizing delete, so it will be useful also for that. Imagine you have two tables, parent and child. They are related with a foreign key constraint, and you need to delete a row from the parent table, one row from the parent table. And how to solve this? Because constraint must be enabled all the time and guard your data, consistency of your data. So we could do a plain delete of a parent table, but under the hood, SQL needs to check will this constraint be valid after this delete? So it needs to check, are there any rows of the child table? And to search for child rows, implicitly, SQL will do a full scan of the child table if there is no index on the foreign key column on the child table. And that is, if child table is huge, it will be super slow. So in order to make this delete faster, we will need to create index on child table foreign key column. Okay? We might think maybe we could use trigger. So with a trigger, we maybe could delete first child rows and then delete the parent. But that wouldn't be very good because, as you know, triggering code within the trigger is always part of the transaction that initiates the trigger, the triggering statement. They're all in the same transaction, same big transaction. Entire time they are holding locks on these rows, keys, objects, and they are releasing the lock when transaction commits or rolls back. But it's a huge transaction, long-lasting transaction. And locks are held a very long time. And if you hold the locks for a long time, there is a greater chance that somebody else will try to access the same table and they will be blocked. So if you will have huge blockage and slower system. Somebody can say, yeah, triggering code in the trigger is exactly the same as outside of the trigger. Yes, it is. Execution plan is exactly the same. Yes, it is. But performance is slower, not because it's a worse execution plan, but because of these blockages. You get blocked and you wait and everybody waits and the whole system gets slow, becomes slow because of these blockages caused by the trigger. A cascade delete. You may say, okay, I will create a foreign key on the child that references parent with on delete cascade. It sounds tempting, but the same problem occurs as in trigger. You have that transaction, when you delete the parent, it's implicit transaction which also deletes all the child rows. And if you have a lot of child rows, that's a huge transaction that lasts for a very long time. You hold locks for a long time there, and everybody is blocked, and your system gets very slow. So you need to avoid cascading foreign keys. Unless child table is super small, then you can get away with cascade delete. So what to do? Do we have some better option? Maybe with procedure. Let's say we create a stored procedure to delete parent row, but we first delete child rows and then parent row, and then we commit. So we use explicit transaction, begin transaction, delete child rows, delete parent row, commit. Sounds right. But the same issue as before. We have a long-running transaction which holds lock for a long time. You have blockage and entire system gets slow. Not good solution. Maybe we should say, let's remove the transaction. Okay, we have delete of the child, delete of the parent, and no transaction. Well, because deletion of the child is basically, deletion of the parent is nothing. Deletion of the child is long-running deletion, and that deletion itself, although implicit transaction of only that statement, that deletion is a long-running transaction. So you will get everybody is blocked on the system, basically. So this is also not a good solution. We need to do something else, and that something else tackles the problem not just of long-running transaction, which blocks everybody, but also another issue which is called lock escalation. Lock escalation occurs when you change rows. For example, you insert or delete or update more than 5,000 rows at once. At first, only rows will be locked exclusively. Key lock, key lock, key lock. And when you pass this threshold of 5,000, it's a bit fluid threshold. It's not always 5,000, but let's say around 5,000 key locks or page locks. Then SQL Server decides, okay, I see a bunch of locks here. It's maybe better to lock entire object. And that's called lock escalation. Entire object gets locked. All the individual locks, key locks or page locks, are deleted and replaced with only one lock, which locks entire table, entire object. And nobody can access that table anymore. I mean, they can select if you enabled RCSI on the database, but basically no changes are possible anymore. Everybody waits, everybody's blocked. So we need to stay below 5,000 rows at a time to escape from this lock escalation issue. So that is what we need to do, and we will do it in the demo. So we will first do in the demo something that is not quite good, and then we will do it proper way, the best way. Table already created, which is a parent table. It has only ID, parent ID, which is identity, 1, 2, 3, name, and we insert 5 rows there, A, B, C, D, E, 5 rows only. And then we have a child table, which is huge. It has many rows. It has child ID, which is also identity, like primary key. And we have foreign key, which is called parent ID. And that foreign key references our parent table. We have some other data like address, and other data could be anything. I put there just bytes to fill the space. Then I inserted into this child table 1,000,000 rows, which are random generated. Parent ID is 1, 2, or 3, random number. Some random address like GUID. And I ran that 3 times, go 3. And then we get 3,000,000 rows. Then I created this index on the address field. And let's see what is the used space of that table. It has 3,000,000 rows. It has around 2 gigabytes. Okay, now let's see the data. First, parent table, and then first 100 rows of a child table. Parent table has parent ID 1, 2, 3, 4, 5, A, B, C, D, E, and the child of 3,000,000 rows has child ID 1, 2, 3, 4, 5, parent ID, which is a random number 1, 2, 3, and some random address and other data. Okay. Now let's see the data distribution of the child table grouped by parent ID. We have 3,000,000 rows, but each parent ID should be around 1,000,000 rows. Let's see. Yeah, so I have around 1,000,000 rows for each parent ID. Total sum is 3,000,000 rows. So let's delete one row. Deletion of one row in a small table, parent is a small table, 5 rows only, and we delete by primary key. That row is found super fast. It should be in instant, in the blink of the eye. Let's see if it is. Start. Not finished yet. 5 seconds. 5 seconds. I mean, that's way too slow. Modern processors in 1 millisecond do 5 million clock ticks, or at least 2-3 million clock ticks in 1 millisecond. Each clock tick can be 32 or 64 instructions. So 1 millisecond is like forever. And this took 5 seconds. That's super slow. So why it is so slow? Let's see execution plan. Now if you look here, we had nested loops that first finds a row from parent table, row we need to delete, but then it also searches through child table. Searches to child table to find do we have matching rows in the child table. But that search is a full scan because we didn't have index on the child table. And that's why it takes so long. It reads 3 million rows and to read 3 million rows is slow, even though we need to delete only one row of the parent. It needs to check the child. We don't have index and it reads full scan the child. Big child, it takes forever. Super slow. So what we need to do? You guessed it, we need to fix it by creating index. So we will create an index on the child table on the foreign key column. Once that is done, let's check again execution plan. It looks similar, but look at the difference. Now it is also checking the child table, but we check it with index seek, and it is going to use this R index we created just now on parent ID column, and it is seek operation. It will very fast go through this tree, index tree, and find the row if it exists. It will be super fast. So let's see. Is it really super fast? Let's execute this. Execute. Yes, immediately, like this. Great. But what if we delete parent ID 3? Failed. Why it is failed? Because child records do exist for this ID. Now we need to get rid of these rows. We already discussed that trigger is not a good solution because it's a long transaction. Cascade delete is also not a good solution because it is a long transaction, blocking everybody. You get slow system, not good. So we need to delete with procedure, and we need to use some knowledge about lock escalation, but first we will do it the wrong way. So this procedure is creating a transaction and then deletes child rows from child table for that parent ID. And then when that is finished, it deletes one row from the parent and commits. We need this set exact abort on because if timeout occurs, that is untrappable. You cannot trap it in T-SQL. Even if you try catch, you cannot trap that. Exact abort on makes sure that it will be rolled back when error occurs, because otherwise, without that, if it is off, then commit or rollback is decision of application. Application gets opened transaction, and if you do nothing, you will leak transaction. You will leak transaction randomly, and it's really a weird issue to diagnose, and it's solved like this. So let's delete that one row. We are deleting one row. You see how long it takes, but in other session we will try to insert the table, insert a row into child table. Let's insert it. Wow, it takes forever. Why it takes forever to insert a row? Let's see, execute. On child table, on entire object, entire table is locked with exclusive lock. And that's why our insert waits. Insert cannot do anything. So you see, insert took 13 seconds. It basically was blocked entire time until our long delete finished. Everybody waits until your delete finishes because entire object is blocked because of lock escalation. So we need to avoid it. That's why in the next example, in the next procedure, we will do it differently. We will say, okay, we won't use explicit transactions. We will use a loop, and in that loop, we will delete 4,000 rows at once in one SQL command, in one delete command. And it is similar to select. You see, from, where, you could have some joins here. Only this part before from, you change it from select to delete top, as you top some rows, and alias. You could also use update, for example. That's very nice, neat trick to change select to update or select to delete. Even more complex joins, etc. So after it deletes, we check rows affected. If records affected are 0, that means we deleted already everything, nothing more to delete. and then we exit loop with break. It exits loop, child records are all deleted, and then we delete the parent record and we are done. So let's see how it works. Let's run it. First, we will check, we'll have 2 million rows, around 2 million, parent ID 1 and 3. So we will delete parent ID 1. Okay, now it deletes, and let's try to insert rows. Insert works. Insert. It's not blocked. Why it's not blocked? Because, let's see. You see, our child table is not locked anymore. Not with exclusive lock. It is locked with intent exclusive. This intent means somewhere down the hierarchy, you have exclusive lock. So you have intent lock on the object, intent lock on the page, and exclusive lock on the key, for example. So that intent means we are locking something below the hierarchy. You have object, page, key. Okay, this deletion finished already, but you know we don't have transactions here. So what will be if this is interrupted? We don't have a way to roll it back. But we can simply resend the request. If it is interrupted or ends with error, application should run again, the same query again, the same procedure again with the same parameters until it is finished successfully. So let's simulate that. So I will run deletion with parent ID is 3. Then I will break it. I will stop it. Let's check now the rows. Yeah, it's not 1 million anymore. So let's call that again. So I'm interrupted. As application, I will resend the query. I will re-execute with the same parameters. It runs. It continued where it left off. Let me check. I will interrupt again and let's check. Yes, it is decreasing. So eventually it will delete all the child rows and then parent rows and we are finished. So it can be interrupted as many times as you like. You can always re-execute and it will continue exactly where it left off. Brilliant. So that's a really good thing. So in summary, don't use triggers. Triggers create huge transactions, holding locks a long time that creates blockage and completely, it can halt to a stall your entire system. Everyone who accesses this table is blocked. Everybody waits. Only one session works. That's to avoid. I mean, you can get away with triggers if that trigger fires almost never and the code in the trigger is super fast, it's short. Maybe, but better to avoid them. We have so many other options. If you need to track changed rows, we can do that with change data capture. That is included in standard edition of SQL from SQL 2016. Before that, it was in Enterprise Edition. You can use change tracking. You can use row versioning. You can use dates. You can use identities. There are tons of options to recognize changed rows. So don't use triggers, please, unless you really have to. Don't use cascade foreign keys. Cascade foreign keys, they create huge transactions, blockages, slowness. Don't use it. You may get away with it if child table is super small, but it's a bad habit. It's better for the habit's sake to immediately do it proper way with procedures, as you will see. So create index on a child table foreign key column. You can get away without index if child is small or you never delete parent. What we need to do is use a store procedure for deletion, use a loop that deletes 4,000 rows at a time with one command, one delete command, not 4,000 single row deletes, one command with 4,000 rows delete. And until all rows are deleted, then you delete the parent. So you, from the bottom up, you basically delete from the bottom up. When topmost parent is deleted, you're finished. It can be, application must be written in a way to re-execute the query if error occurs, so it can continue where it left off. no lock escalation, no long transaction, table is not locked. Everybody can insert, update, delete at the same time, super fast. System is much faster than before. Great way to do it, right? Bonus tips. What is the most frequent command your database is getting? It is by far select. Select is like 99.9% of all the commands your system gets, probably, typical system, OLTP especially. And the second place is insert, and then third place is delete and update, sometimes delete. That's typical. That's typical system, so it should be, this yellow part should be even smaller, maybe tiny line like this, like a hair. That's more realistic. So select is vast majority. What that tells us? That tells us that changing the data is only on few places. Insert, up, delete is not that frequent. It's not that much of the code. So we can rewrite this code to use stored procedures. And it's not a lot of work. That's the beautiful thing. So you can create, with not so much effort, you can create stored procedures for changes, for insert, up, delete, of your objects, not for table, for objects, because one object may consist of multiple tables, and you insert to all of them. So you create stored procedures as a first step. What it brings you, what benefit? Why would you do it? Because you can improve security. How? To account that application uses, SQL account that application uses, you reduce privileges and you give it only two privileges: select and execute. Execute, that means it can execute stored procedures, functions, etc. Select means it can select tables. You can grant it to entire database, these two privileges, or to schemas, DBO and some other schemas you use. Schema is maybe bit neater way to do it. And what that brings you, it is much safer. It is much harder. I mean, attacker who takes over your application cannot anymore drop tables. It cannot alter tables. It cannot delete you data, change rows. It is forced to do it through stored procedures, and that's less likely to do. Especially you can do some checks in stored procedures and you can detect such things and you can bounce these attacks. It's super safe. Another benefit, you can say, oh yeah, I cannot abandon triggers because I don't know who will change the data. With this approach, you know who will change the data. Stored procedure is the only place to change the data because nobody else has privilege to change the data, because application has only select and execute on procedures. So it doesn't have a choice. It must use stored procedure. You're certain of that, and you can implement any logic in that stored procedure with smaller, shorter transactions than it would be if it was a trigger. Great benefit. And you also avoid cascade delete of the foreign keys. You have less round trips because stored procedure has multiple statements, and they are all in one call, in one round trip executed. That's much faster than if you constantly over the network do call. That's slower than one call. So another benefit, it's a bad thing to open transaction from the application side because you go back and forth and network is not 100% reliable, and you can get weird things with transactions opened from the application side, then you do some stuff, then you commit or rollback. It's much better to open transactions from the stored procedure side, do your changes and commit immediately as one unit, one call. That is what you want to do. Then it's atomic. Then it doesn't depend on the network, on the call, on multiple calls, round trips. It's much safer and much more reliable. Do it like that. So another benefit, it's when something occurs, some query is slow, it's inside procedure. If it is inside stored procedure, you can give it to DBA or SQL developer, and they will fix it, they will optimize it without spending the time of the developer anytime. So it's cheaper, it's faster to bring new features, to optimize the system. It's much faster with less effort, with less cost for you. and your users will be more happy to receive new features and better optimization sooner than people who don't use this principle, because you can deploy just that one procedure instead of compiling entire application and do a full deploy. It's much faster, easier to fix. Great benefit. You move much faster. Thank you very much. If you have any question, that is my email. If you want to optimize your SQL Server system, you can drop me a message. And thank you for listening. I've been enjoying in recording this, and see you in the next video. Bye.